Alright guys, so in this part of the chapter we are going to talk about the most important concept that you have in this chapter, which is basically the electrophilic addition of alkenes. Okay. Once again, the topic that we are going to talk about is electrophilic addition of alkenes. Okay, so this is the most important reaction when it comes to alkenes. This is the most important reaction when it comes to alkenes. And then in this part of the chapter we are going to basically talk about the general reaction mechanism for electrophilic addition. So we are going to talk about the general reaction mechanism for the electrophilic addition, and then we are also going to talk about how the electrophile, okay, whatever the electrophile is, it could be the hydrogen or it could be anything, okay, but in the first reaction we are going to talk about HBr. So we will talk about how the pi bond of the alkene is going to attack the electrophile, and then we will also talk about the production of the carbocation as an intermediate. So we will talk about something called carbocation, and then we will also talk about the carbocation being an electrophile and then reacting with the remaining bromide ion in the mechanism. Okay, so we will talk about these points in this particular lecture note. Alright, so here is the mechanism for the reaction between alkene and HBr. Okay, so I'm not going to use the same exact molecule, but in here you have 2-methyl propane. Okay, 2-methyl propane. Okay, so 2-methyl propene. Okay, so I'm going to use a propene. Okay, simply I'm going to use propene. Okay, here is my propene. Okay, so you will have something else other than what you have in your textbook to refer to. Okay, and the reaction between propene and HBr. This is what we are going to talk about as the first electrophilic addition reaction. So let's break down the title for this reaction. It is electrophilic addition. So it is the addition reaction, right? We are interested in the addition reaction. So what is addition reaction? What is addition reaction? You are adding something new, okay, without removing any existing atoms or group of atoms, right? That is called addition reaction. In addition reactions, you are adding something new without removing any existing atoms or group of atoms. Okay, that is what we are going to do. Okay, so that is called addition. And what are we adding in this reaction? We are adding an electrophile. So basically electrophile, we usually use the term E+, which means, it is electron deficient. Okay, that is why it loves electrons, right? So electrophiles are electron deficient. Usually positively charged atoms or partially positively charged atoms are the electrophiles, right? So electrophiles are electron deficient and therefore they love electrons, right? So we are adding an electron deficient species to the double bond, to the alkene. That is what we are going to do in this reaction. Okay, that is what we are going to do in this reaction. So let's get to it. Okay, so once again, our molecule is propene. Okay, so in your textbook you have 2-methyl propene. Okay, but I'm going to use propene. Okay, so basically if you take a look at propene, the condensed structure of propene, this is the skeletal structure of propene. The condensed structure is basically CH3, CH2. This is the condensed structure for propene, in case if you are wondering. Okay, but by now these are easy for you. Okay, and then we are reacting it with HBr. What do you know about HBr? What do you know about this HBr? Is it a polar molecule or a non-polar molecule? Is it a polar molecule or a non-polar molecule? Don't look at my face now. It's a polar molecule. Of course it is a polar molecule. Okay, it is a polar molecule. Why? Because you have a bromine attached to hydrogen. What do you know about bromine? It is a halogen. Halogens are very greedy towards shared electrons, right? Halogens are extremely greedy towards shared electrons. So bromide, whenever it is sharing electrons with an atom like hydrogen, it has a high electronegativity, which is basically the electron greediness. Okay, so bromine has a very high electronegativity, so therefore bromine is trying to push these shared electrons towards bromine. Okay, towards bromine. Because of that, bromine has a partially negative charge, okay, and hydrogen has a partially positive charge. So HBr is a polar bond, HBr is a polar bond. Okay, so this is the dipole moment for HBr. HBr is a polar bond, and then it is polar because of the electronegativity difference between hydrogen and bromine. Bromine being very greedy, it is pulling these shared electrons towards bromine, making hydrogen electrophilic. By making hydrogen electrophilic. Why? Because hydrogen is electron deficient. Hydrogen is electron deficient. So basically, in HBr molecule, hydrogen is the electrophile. Hydrogen is the electrophile. So basically, this hydrogen right here is your electrophile. This is your electrophilic group. Okay? So this is your electrophile. This is your electrophile. Okay? So we know that. And we have to add hydrogen to our alkene. Okay? So where do you add it? You are adding it to the double bond, because that is what you use to add something new, right? Without losing anything. If you want to add something new, like in addition reactions, you will use multiple bonds. In this case, we have a double bond. So basically what happens is that I'm going to remove these partial charges, because it should be in your head, not on the paper. Okay, you know now that hydrogen is electron deficient, and then double bond is electron rich. Double bond is electron rich, so double bond is going to attack this hydrogen right here. Here's the thing, so double bond is offering a new bond to hydrogen, right? Hydrogen needs only one bond. Hydrogen needs only one bond, so hydrogen has to give up this bond if he wants to accept this new bond. Okay, HBr is like a bad marriage. Bad marriage. Why? Because even though they agreed to share 2 electrons between hydrogen and bromine, bromine is always pulling all those 2 electrons, the shared electrons, towards bromine. So hydrogen is already stressed. Hydrogen is done with bromine. Okay, so hydrogen is waiting for someone to donate 2 electrons and make a new bond, so that he can say, okay, go away, I don't need your electrons, right? So that is exactly what happens when double bond attacks the hydrogens with 2 electrons. Hydrogen will get rid of these electrons, and then those 2 electrons will go onto bromine. Okay, will go onto bromine. So what you have now is something like this. Okay, here is your molecule, but remember, I just removed the double bond. I just removed the double bond, and then here is your new hydrogen on this atom. I don't have to draw it, but I'm going to draw it. Okay, here is your new hydrogen, and then this carbon is fine. It had a double bond before, and now it is getting a single bond in that place of the double bond. So this hydrogen is happy. But this carbon is happy. But look at the center carbon. It had a double bond before, and we broke that double bond from that carbon, and now this carbon is losing a bond, right? He lost a bond. This carbon lost a bond. So therefore, this carbon is positively charged. This carbon is positively charged. You broke a bond from the carbon, the middle carbon, and then you didn't give anything to it, right? You didn't give anything to it. So therefore, that carbon is positively charged. So this molecule, this ion, we call it carbocation. Okay, we call it carbocation. Okay, we call this carbocation. Carbocation. And then what you have in the medium is the bromide ion. You also have the bromide ion in the medium. Bromine is happy now. Why? Because it took both electrons from the shared bond between hydrogen and bromine. Okay, so it is bromide. And now carbocation is positively charged, so it is deficient in electrons. So carbocation is electrophilic, right? Carbocation is electrophilic, and then bromide anion is nucleophilic. Okay, So once again, this bromide could attack the carbon in the middle, and then you will get the final product, which is this. This is what you get. Are we clear? Alright, so this is your final product. Here's what happens, guys. Okay, once again, let's go through it. Okay, so this electrophilic addition of HBr is a two-step reaction. It is a two-step reaction. You're asking me where are the two steps? Here is the first step. Here is the second step. So this is a two-step reaction. And during the first step, what we do is we are using the double bond and attacking the electrophilic hydrogen. Okay, and then the two electrons that were shared between hydrogen and bromine will go onto bromide and form the bromide ion. Okay, so since the double bond attacked the hydrogen, it is getting a new hydrogen. Okay, so you have the hydrogen on this corner carbon, okay, on this carbon right here, but this middle carbon didn't get anything. It used the electrons but got nothing, right? So therefore it is positively charged. So therefore we call it carbocation. Carbocation. And then carbocation is electrophilic, bromide is nucleophilic, so you can have a reaction between bromide and the carbocation. The bromide will attack the carbocation, giving you this particular product. Okay, so that is the mechanism for the electrophilic addition of HBr to alkenes. Okay, so this is the mechanism for the electrophilic addition of HBr to alkenes. Let's look at the slide for a minute. Okay, so once again, this is a two-step reaction. Okay, so energy diagram should have two steps. Okay, and then your intermediate is going to be your carbocation. Okay, that is that resting point near the two peaks. Okay, so you have the carbocation intermediate in that small dip near the top. Okay, and then of course the activation energy for the first step is very high. Okay, so first step is slow. This first step is slow. Why? Because of the activation energy is high. If you ask me what is activation, that is the energy gap between the starting materials and the first transition state. Okay, that is your first activation energy, and the second activation energy is very small. Okay, that is the gap between the intermediate and the second transition state. So the activation energy for the second step is very small. So that is a very rapid reaction. So this is very fast. Okay, so this first step is very slow. That is why you have a huge activation energy. But once you have the intermediate, the second step is almost immediate. Okay, and then the overall reaction is exogonic. Exogonic, that means, you know, the product energy is lower than the starting material energy. Okay, so this is a spontaneous reaction. Okay, this is a spontaneous reaction.
You said the overall is exogonic.
What?
You said the overall is exogonic.
Exogonic, yeah, because it is releasing energies. If you take a look at the energy diagram once again, starting material energy is greater than the product energy. So you are basically releasing energy. So delta G naught is negative. Look at this delta G naught right here. This is negative. So this is exogonic. Of course, you can expect similar reactions. I mean, between alkenes and things like HCl or HI. Okay, so basically, instead of having a bromide, you can have an iodide or a chloride. Okay, so you can have similar reactions using HCl, HI, or even water. Okay, so these are very similar reactions, but HI is usually generated using potassium iodide and phosphoric acid. Okay, so in the exam, if you ever want to make an addition reaction for HI, rather than writing HI, you can use Ki and H3PO4 as the reagent. But HCl is very straightforward, just like your HBr. Okay, just like HBr, HCl will work. And then now this is the more important part. This is when the fun starts, okay? Fun starts, okay? Let's take a look at what we did before. So I reacted this alkene with HBr, and then in this reaction you added a hydrogen to this carbon at the end, right? And the bromine goes to the middle carbon, okay? But did you ever wonder why I put the hydrogen on the carbon at the end and why you put the bromine in the middle? No, right? You never asked that question from me. I mean, I could have drawn it like this because I mean we use this double bond, so the hydrogen could come to this carbon and then the bromide could go to this one, right? So there are two possibilities actually, right? For this reaction, there are two possibilities, right? But when you take a look at the reactions, okay, if you do this practically, you will realize that you almost never see this second product. You almost never see this second product. You only see this first one, okay? You only see this first product. So therefore we call that this reaction between propene, okay, and HBr is regiospecific. What is the word? Regiospecific, which means when a reaction can give you multiple products, okay, more than one product, reaction typically favors only one product, okay? In this case, this one right here on the top, that is the favored product, okay? So this product is favored and the other one is almost never formed, okay? So why do we have this favoration, okay? So this favoration for one of the products is called regiospecificity. And if you take a look at the other reaction that you have in this slide, okay, I have 2-methylpropene reacting with HCl. Once again, the chlorine goes to the middle carbon right here. Chlorine goes to the middle carbon and the hydrogen goes to the carbon at the end, okay, giving you this 2-chloro-2-methylpropane, okay? And you never get the other product where, you know, chloride goes to the carbon at the end and the hydrogen goes to the middle carbon, okay? You never see the other product. So this reaction is regiospecific. To explain that, we use a rule called Markovnikov rule, okay? Of course, he is a Russian scientist, that is why, you know, the names usually end with V, okay? You spell it, I mean, you pronounce it as Markovnikov. Hopefully I'm right, okay? I think I'm right, so it is Markovnikov, okay? Markovnikov rule. So this is what Markovnikov said. Listen and learn. It is a very easy mechanism, okay? This is exactly what Markovnikov said. Madison, pay attention. Alright? So this is what Markovnikov said. Not in his words, okay? Not in his words. Markovnikov said hydrogen is like money. What does hydrogen like? Money. Hydrogen is like money, and usually money goes to the person with more money. Am I correct? So usually in the world, rich gets richer, right? Poor guy gets poorer. That is exactly what happens in the world, right? Mainly because, you know, when you are rich, you can invest your money and then get richer, right? But doesn't matter, right? So according to Markovnikov, he never said that in his, you know, words, but according to Markovnikov, hydrogen is like money, okay? So when hydrogen goes to a carbon, it goes to the carbon with more money, or in other words, it goes to a carbon with more hydrogens, okay? So look at the molecule that we have on the board. It is a CH3 CH2. This is the compound that I have on the board, okay? Clearly, by looking at the two carbons, you can say that the carbon at the end, the CH2, that is rich. Let's call it R. This is your rich carbon. Why? Because it has more money. In other words, it has more hydrogens, right? So the middle carbon has only one hydrogen. It is a CH. So this carbon is poor. This carbon is poor. Okay? So when usually for certain, I mean, sometimes these carbons could be equal, then that is perfect. You can pick your carbon and give a halogen and the other carbon gets the hydrogen. Get it? But sometimes you can have two carbons that are not having equal amount of hydrogens. If that is the case, you can always identify them as poor and rich carbon. The carbon with more hydrogens, hydrogen is like money, right? So the carbon with more money is of course rich. The carbon with less money is poor. Do we get it? But hey, don't put this R and P in your exam book. This is for understanding purposes, okay? If you put R and P on your book, people will think that you are weird, okay? So don't do that and they will mark you wrong, okay? So you know, this is your poor carbon, this is your rich carbon. Okay, so you are adding what? You are adding HBr. You are adding HBr. So you are basically giving hydrogen to one carbon and the bromine to the other carbon. Okay, so according to Markovnikov, hydrogen is like money, it goes to the carbon with more money. So hydrogen goes to what carbon? Rich carbon, the CH2, right? So your product will have the CH2 gaining another hydrogen. So this will be CH3. And the poor carbon has to get something, right? Because it gave you the double bond, right? So it will get the bromine. So this will get the bromine. Do we get it? Exactly. So what do you have to remember? When you are adding something to alkenes, okay, when there is an addition reaction, especially if you are adding two different atoms or groups to your alkene, okay, you consider hydrogen as money, okay. So when you are adding hydrogens to an alkene, hydrogen prefers to go to a carbon with more money, or in other words, hydrogen, okay. Do we remember? Never forget that, okay. So in the exam, don't be like, oh my god, what did Markovnikov say? I don't remember. No, it is very easy to remember, okay. It is very easy to remember. So let's look at the molecule that you have in the lecture note. You have 2-methylpropene. Of course, pay attention to the two black labeled black color carbons, okay. Okay, so pay attention to them. Of course, the center carbon right here, that is the poor carbon, because it has no money, no hydrogens, right? So here's the poor carbon right here, poor carbon. See? And here is the rich carbon. So according to Markovnikov, when you're adding HCl, hydrogen goes to the carbon with more money, or in other words, hydrogen, right? So this carbon becomes CH3, and the middle carbon gets what? The chlorine. Okay, so middle carbon gets the chlorine. Do we get it? But hey, honestly, Markovnikov said nothing about money, okay? This is what Markovnikov said, okay? When you are adding something like HX, X could be anything. It could be a halogen, an OH, or anything, okay? So in this example, of course, X is a chlorine, okay, or a bromine. So when you are doing an addition reaction of HX to an alkene, okay? So hydrogen attaches to the carbon with fewer alkyl substituents. Okay, this is what he actually said. I mean, this is just theory now to you, okay? You already know what to do, okay? I'm trying to justify or honor what Markovnikov said, okay? That is why I'm mentioning them to you. You don't need them, to be honest, okay? Hydrogen attached to the carbon with fewer alkyl substituents, and the X group, in this case bromine or chlorine, it goes to the carbon with more alkyl substituents. When you have more alkyl substituents, it doesn't have many carbons, right? So basically more alkyl substituents means you are the poor carbon, right? Less alkyl substituent means you are the rich carbon. Okay, that is how I gave you those words into you, okay? So basically this is the technical word. Okay, the reason behind it is the carbocation stability, okay? The reason behind it is actually carbocation stability, which we will talk about in a minute, okay? But look at this molecule right here, the very bottom example, okay, 2-pentene. Okay, so in 2-pentene, both carbons have only one hydrogen, right? So they are both equally rich. Am I correct? Both carbons are equally rich. Okay, so it doesn't matter which carbon gets the hydrogen, which carbon gets the bromine. You know? So of course, both products are possible. Okay, both products are possible. Are we clear? So in this slide, I am restating the Markovnikov rule. Okay, so I mean, once again, this is not important to you because you know the better way to remember this, right? So if you restate it, okay, the addition of HX to an alkene happens in such a way that you will get more highly substituted carbocation. You will get the more highly substituted carbocation during the reaction, okay? Why do we need the more highly substituted carbocation? Because the highly substituted carbocations are more stable. So let's take a look at this example that you have in your slide, okay? So the the one on the top, okay, one on the top, this is the intermediate that you get. So of course this carbocation has 3 alkyl substituents, right? So it has 3 CH3 groups, so it is highly substituted, okay? But if you take a look at the reaction that never happens, okay, basically this is your carbocation where you only have 1 substituent. In the previous one you had 3 substituents on the carbocation, but in here you only have 1 substituent and then 2 hydrogens. So this one is very less stable, okay? So we call it a primary carbocation. Depending on the number of substituents you have on the carbocation, you can categorize them as either primary, secondary or tertiary, okay? Depending on the substituents that you have on the carbocation, you can categorize them as primary, secondary or tertiary. So here is your carbon that contains the positive charge, okay? So this carbon can have 3 additional bonds, right? 3 additional bonds, okay? So if you have only 1 substituent, okay, we call it primary, okay? And then if you have 2 substituents, let's put 2 R groups, then only 1 hydrogen. That is a secondary carbocation, okay? And then if you have 3 R groups, anything other than hydrogen, R is anything other than hydrogen, okay? So this carbocation is a tertiary carbocation. And tertiary carbocations are extremely stable as compared to secondary or primary. And then of course you can have a methyl carbocation like this one. This one doesn't have any R groups, right? So this is the least stable one. Are we good? So the stability of carbocations increases drastically when you are going from left to right. Stability increases drastically. Stability increases drastically when you are going from left to right. Okay? So basically, during the addition reaction of alkenes, it always try to make an intermediate that is more stable. Okay? So basically, if you want to do that, you should always give the halogen or the X group to the poor carbon, or in other words, more highly substituted carbon. Okay, but all these are just some details to you now. Okay, what matters is remembering that hydrogen is like money, and it always prefers to go to the carbon with more money or more hydrogens. Okay, that is all you need to know. Okay, once again, same thing here. Okay, so in this reaction, of course, among the 2 carbocations possible, the top carbocation is a tertiary carbocation, the bottom carbocation is a secondary one. So of course tertiary carbocations are more stable, so the mechanism will take place in this manner, and then you will get a 1 bromo 1 methyl cyclohexane as your product, and not 1 bromo 2 methyl cyclohexane. Okay, so keeping all of these things in your mind, let's see if you could do this worked example. So if you are watching the video, this is when you will pause your video and then see if you could do it. Okay, alright guys, let's do this. Perfect. And explain me your product. Why did you put the bromine on that carbon, and why did you put the hydrogen on the other carbon?
Because this one has the more money.
Okay, more hydrogens.
More hydrogen.
So you gave the hydrogen to that carbon.
Yeah.
Perfect.
And
then the other carbon was poor.
Yeah.
So
and
you
the BO.
Perfect. Well done. So that is a student that listens. Okay.
Extra credit.
Huh?
Extra credit.
Later. Maybe next time. Okay. You should give me extra credit for this one. Okay. Alright. Most people are confused when they discuss Markovnikov in class. Well, you guys should be. I mean, I thought that you guys understood it, and apparently not everyone, right? So here is your compound. Here is your compound, and then first of all, in your head you will identify the rich carbon and the poor carbon. Okay. So here is your rich guy because it has 2 hydrogens. Okay, and then here is your poor guy, which has no hydrogens. Okay, so this is the poor carbon, this is the rich carbon. Okay, so what you do is you will break the double bond You will break the double bond, okay? Once you break the double bond, you have to give something to it, okay? What we are giving here, and a hydrogen and a bromine. Hydrogen will go to the rich carbon, so you don't have to write anything. And then bromine will go to the poor carbon. So this is bromine. Okay, this is your product. The same as what he wrote, okay? I mean, this is a CH3. You know skeletal diagrams, right? Alright, so that is how we do it. And here is your solution. I mean, I don't have to show you this. Obviously, you have to have it now. Let's see if you could do this study check. There will be two possibilities, to be honest, okay? You can have two possibilities for this one. You could have two possibilities. If you are watching the video, this is a good time to pause the video and try this by yourself.
Come on now.
Well done, that is one possibility. Does anyone have a different answer? Yeah, go to it. Good job, Gabby. You mean CH3? CH2, CH3?
Okay.
Alright. What is the difference? No, that is not correct actually, okay? The second one is not correct. I mean, these two look alike. Only difference is that you put a hydrogen here, or you should not have a hydrogen there, because this carbon already has two bonds from the double bond, and then one bond to the hydrogen, that is 3, and then you need another bond to attach to this carbon, right? So that is 4. So you only need one hydrogen. So this is not correct. Okay. So by the way, the top one is correct. What Gabby did was correct, and then the only problem it has is that, you know, don't draw the arrow this side, because I mean the arrow should be the other side. So yeah. So this is how we do it. But I mean, this is not that hard, okay? Some people are, oh my god, I'm so confused. No, don't be, okay? This is not hard, and this is how you think. You know you are adding HI, right? You are adding HI to a double bond, okay? So you simply have to erase the iodine because you added it later, right? So you know this carbon had to have a double bond, okay? This carbon have to have a double bond with what? With either one of these two carbons, because you can't have a double bond with someone so far away. It has to be the immediate neighbor, right? So you have two different kinds of immediate neighbors, okay? So here is an immediate neighbor. Let's call it 1. I mean, both these are equal, so I'm going to call both of them 1, because both those carbons are chemically equivalent, okay? And here is the other neighbor. So Gabby chose to make a double bond with this neighbor. So she did something like this. Okay? But if you want to make a double bond with the other neighbor, you can. You can do it. So it will kind of look like this. It will kind of look like this. Are we good? So both these are possible starting materials. Both these are possible starting materials for the product that is shown in the work example. Once again, guys, in these two things, here is your poor carbon. I'm going to put a P here. This is your poor guy, and here is your rich carbon. So when you add HI to any one of these two, they will give you the compound that we need. Yeah, medicine, go ahead.
So, like on the test, did you ask us to do the two possibilities or the third possibility?
They are both okay, because they are both logical, because you know you are adding an iodine to the poor carbon, and you are adding a hydrogen to the rich carbon. So both these cases will basically give you the same exact product. Okay, so they are both equally possible. They are both equally possible. So both are correct. Okay, both these things are correct. So write it down, guys. Write it down if you don't have the correct answer. So now in the next few slides, we are going to talk about the stability of carbocations. Okay, carbocations. So as you already know, carbocations only have 3 bonds. It only has 3 bonds. It only has 3 bonds. So the stability. I'm sorry about that. Let me fix it. Alright, so during the next few slides, we are going to talk about the carbocation stabilities, guys. Okay, so basically carbocations have only 3 bonds, and it also has a positive charge. So when you have only 3 bonds, the best way to put the 3 bonds is in a trigonal planar geometry, right? Trigonal planar geometry. So basically carbocations have a geometry like this. It's a trigonal planar geometry. Okay, so remember the sp2 hybridized carbons. That is the same thing. Okay, trigonal planar geometry. So this is your carbocation, and the bond angle is approximately 120 degrees between each other. Okay, 120 degrees between each bond. Okay, so it has a trigonal planar geometry, and then this carbon has all 3 bonds on the same plane, and then perpendicular to the 3 bonds you have your p orbital, which carries no electrons, so it is vacant. That is why it is positively charged. Okay, so that is how a carbocation looks like. And the stabilities, we already talked about the stabilities, guys. Okay, tertiary carbocations are much more stable as compared to secondary ones, and the secondary carbocations are more stable as compared to primary. And then when you have a methyl group, it will be the least stable carbocation. Why? Because when you have more substituents or R groups, okay, they donate or push electrons towards the carbocation. Okay, they push electrons towards the positive charge on carbon, and therefore you can reduce the intensity of the carbon positive charge. Okay, that is how it makes the carbocation more stable. That is how it makes the carbocation more stable. So whenever you have more substituents on the carbocation, okay, those substituents or methyl groups can push electrons towards the positive charge containing carbon, and therefore it is less intense. It is like this. Let's say positive charge is an instability. It is like having a huge loan. Okay, you borrow some money. Okay, and then let's say you have some good people around you, good friends around you, and then they pitch in to pay the loan somewhat so that you don't have to pay the interest as much. Okay, so these good friends are actually your R groups or substituents. Okay, so they basically push electrons towards the carbon that contains the positive charge, and therefore the positive charge intensity will be less, so therefore it will be more stable. So more R groups or methyl groups you have or alkyl groups you have, the more stable the carbocation is going to be. Okay, so this diagram basically explains the stability using dissociation enthalpies. I mean, if you talk about the carbon-chlorine bond, if you talk about the carbon-chlorine bond for these 4 compounds, okay, the dissociation means, you know, letting this chlorine go, okay, and forming a carbocation, okay, forming a carbocation. So the energy, the dissociation energy is low if carbocation is more stable. If carbocation is more stable, the dissociation energies are less. Okay, so as you can see, the final product, the CH3 thrice CCl, has the lowest dissociation energy. That means it is okay with chloride leaving the carbon, because you know the carbocation you get after the removal of chloride is more stable. Okay, so if you have no R groups, okay, like the CH3Cl, then you know the carbocation that you are going to form after the removal of chlorine will be highly unstable. So the dissociation energy is very high. It is like, imagine that the dissociation is like getting a divorce. Okay, so carbon and chlorine has a marriage. Okay, so now you're going to break the bond between carbon and chlorine. So you're basically going to divorce the carbon and chlorine. Okay, so carbon will let chlorine go easily if carbon knows that, okay, I'm getting some support from my family members and friends, right? So it will be like, okay, go away, I don't care, right? So you can go away. If you really don't want me, you can go, right? But let's say CH3Cl has no family members, right, that are supportive, right? So no alkyl groups to stabilize the CH3Cl. So that carbon is holding on to the dear life for chlorine, right? So don't go. I mean, I'm not letting you go. If you go, I mean, I'm not getting any money from you, so I don't want to let you go, right? So I don't have much support. So that is why dissociation is very hard. The energy. So if you want to break that marriage, I mean, they're going to hold on. I mean, they're going to get every penny before they divorce you, right? So basically, that is why the dissociation enthalpies are high. Do we understand now? So if you have more support, it's like, if you have 3 jobs and you don't care whether, the money that you get from the, a divorce, then you can be like, okay, go away, I don't care. Okay, so that is exactly what happens. The more R groups, the more support, so that the dissociation is easy. Why? Because the carbocation is more stable. So in here, I mean, by now I'm explaining the same thing in many different angles, okay? So basically, if you have more and more R groups, okay, more substituents on you, the positivity or the intensity of the carbon, I mean, blue means, you have a very intense, I mean, these are electron density diagrams, okay? So usually in electron density diagrams, we use blue color to denote positive charge, and then we use red color to denote negative charge, right? So as you can see, the positive area is very small when you have a tertiary one. But when you have a primary or a methyl one, you have a huge positive area on carbocation, right? So they are highly unstable. Okay, so all these things happens once again through hyperconjugation, which we discussed before. So whenever you have more R groups or alkyl groups, they will push electrons or donate electrons through the sigma bonds, okay, making the carbocation more stable. So we already talked about it. So by now you should be able to do this worked example by yourself, okay? So if you're watching the video, you can pause the video and do it. And if you're in class, you can do this example at home, okay? I'm not going to spend time doing this once again. Why? Because clearly in this compound you have a poor carbon and a rich carbon, okay? So by now you should be able to write the product, okay? So pause the video and try it if you are watching the video at home. So this will be your answer. This will be your answer. And then the next few slides are going to be about Hammond postulate, okay, which is basically about the morphology of the transition state, okay, which we will discuss later on, okay. So with this, I'm going to terminate the video, and we will talk about the Hammond postulate in a minute.